Hi and welcome to the next video on Linux device drivers. So in this video I'm going to talk about how to write a simple character driver module. Okay, so before we go, let's see a quick introduction of what a character driver is. So like we discussed in one of the first presentation. So I think it's first easy to explain a block device driver, and then we will try to understand what a character driver is. So block device driver is basically any device on which you can mount a file system. Like for example, your pen drives, hard disk, CD-ROM drives, etc. So the main advantage of a block device driver is, so if you access a particular file, so you can go back and forth. So for example, if you're watching a movie, you can skip a song and go to the next scene, or you can go backwards and see a particular scene again. So that's a block device driver. So in comparison to this, character device driver is one wherein you get a stream of bytes and you consume the data as it comes in. More like real-time data. Like for example, you can talk about a keyboard, a mouse, a camera, etc. Wherein the data just comes in, so you don't have an option of going back and forth. So you consume a data as it comes in. So that's basically a character device driver. So we will just see a quick program, so wherein you can see on how you can write a small character device driver. So before I explain how to write a character device driver, so let's see on a few things. So I'm just going to clean up the modules that we wrote in the last session. Okay, so what I want you to understand is in Linux everything is basically treated as a file. So be it a regular file or be it a device. So when I do an ls minus l on a regular file system, so these are all the programs and some of the videos that I've already uploaded. So you see this listing in the ls minus l output. So if you just see on what every column means, so the leftmost column is basically an indication of the permissions. So what is the permission that is given to the user of, the creator of the file, the group to which the user belongs, and everybody else. So it's basically the read, write, execute permissions that you see here. So the second column is typically a 1, for files. So let's ignore that. And the third column is a user, fourth column is a group, and fifth column is the size in bytes occupied on the disk. The sixth column is basically the timestamp that the file was last modified. And the last column, which is nothing but the file name itself. So if you do the same output on the ls, if I do an ls minus l on the /dev directory, and let's see, we see only the head of the output. So what you see here is I have the first 10 entries in the /dev folder. /dev is a in RAM file system. That is, it resides only in the RAM and then gets destroyed on the reboot. So it is a RAM file system in which you create all the device nodes. That's basically the, you can say, like the symbolic links to all the devices that you have on the system. So what you see here is, so for example, if you see the first device, this particular device, if you see this console here, so what you see is the first character, on the leftmost character C indicates it's a character device driver. Then this is a 9-bit field, 9-character field, which indicates who gets read-write access. So then comes one, which is basically one for any particular file, be it a special file or a regular file. Who's a creator of this, to which group they belong to, and let's skip these two numbers for the time being. And then you see the last modified timestamp, and then the name of the file. So if you compare this output with the above output here, which is basically for a file listing. So the top is basically the file listing, and the bottom is basically the device listing. So what you see here is the first, second, third, and fourth column are same, for both the entries, and the last two columns are again same. The last modified name and the name, last modified timestamp and the name of the file. Now what is different is this column, which basically indicates a size of the file in case of a regular file, and in case of a device you see it separated by two numbers. Two numbers separated by a comma. So what is this is basically the major number and the minor number of the device. So Linux associates a /dev file entry to the corresponding driver running in the kernel space by the major number. So the other way of saying, so the major number represents a unique way of identifying a driver which can be associated with a particular device. And minor number basically corresponds to the number of instances of that device. So let me do one more listing here on the /dev directory and search for the hard disk entries. So what you see here is, so I have a system here, wherein I have a hard disk, which is nothing but SDA, and then I have, almost 10 partitions on this particular hard disk. Now, if you see here, so this, the first, second, third, fourth, the fifth column, the first number is basically a 8. So this basically indicates there is a single driver, block device driver responsible for all the partitions on this particular hard disk, which makes sense because we have a single hard disk on the system, and then a single driver is good enough to handle all the partitions on the system. Now, in order to differentiate between the different partitions on the system, so the minor number is used. So 8 indicates a major number which says there is one particular driver which handles all these devices, and the 0, 1, 2, 3, 4 all the way up to 10 indicates the minor numbers which indicate the different partitions on the hard disk. Okay, so that is the basic thing you have to understand. So there's a major number, minor number combination. Major number uniquely identifies a driver associated with the device, and the minor number uniquely identifies the instance of the device. Okay. Now coming back to the programming, so what I'm going to discuss is, the 2.4 Linux style of how to define a character device driver. That's a fairly straightforward approach, so that would probably give you an idea of how to write a character device driver. So what we will do is let's copy example 01 simple module.c as example 07 simple character drv.c. Okay, so I'm just going to open example 7 simple character driver.c, and we will rename example 01 as example 07 to keep the function names in sync with the file names. Okay. And I'm going to include a file called include linux/fs.h for the character driver support. Okay. Now, so this is our driver, which is going to act like a character device driver. So the first thing that you would want to say is, like we have to tell the kernel that we are registering a character device driver. So what we will do is, so let me put a comment here, register with the kernel and indicate that we are registering a character device driver. So the function to be used is register_chrdev. So this basically takes 3 parameters. So first thing is the major number. Okay, and the second parameter is nothing but the name of, let's keep it as name. I'll just tell you where this name gets used. So the name, let's say name of the driver, and the last parameter is something called file operations. Okay, now what I'm going to do is I'm just going to put some random number here. So let's say 240 is my major number, and the name I'm going to give it as simple character drv, and okay, so the last parameter I'm going to put it as example 07 file operations. Okay, let's see what this indicates. Now this is how you would register a simple character driver, and notice that we have done in the module init function. Like, So as soon as this module gets initialized, that is loaded into the kernel space, so the module init gets called, and the module init in turn registers a character device driver with the kernel. Now, if you have any device or device entry in the /dev file system with a major number of 240, so this is a driver that is going to service any access to that particular device. So when the module gets unloaded, you have to do the reverse of it. So we are going to do an unregister the character device driver. Okay, so I'll just say unregister chr dev, give the same major number that you've given in the register character function, and give the same name that you gave above. Okay, so we have successfully registered and unregistered a character device driver here. Now let's come to this last parameter that we pass to the register character driver function. So before I explain what this contains, let's try to visualize what we typically do with a regular file. So for example, if I have a text file, so let's say that let's say the test.c itself. So I have a file called test.c here. So what you typically do with the test file is, so for example, I can open this test file, I can read what is the contents in the text file, and I can close it. Okay. The other thing that I can do is I can open it, make some changes to it, save, that's basically write the file, and then again close the file. So typically what you do is you basically open a file, you perform some read or write operations to the file, and then close the file. You basically do the same type of operations with a device also. For example, if you have a pen drive attached to your device system, you would typically open the pen drive as a folder, or open some files in the pen drive, and then access the files and then save them back on the system, and then close the file. So we do the same thing on a device also. So Linux does not differentiate between a regular file and a device file. So this structure, this third element that we have put here is basically a variable of type. Let me globally define it here, to hold the file operations performed on this device. Okay, so I'm going to say struct file operations example 07 file operations. Okay, now this is basically a variable, so that contains the type of operations that you can perform on this particular device. Now this struct file operation structure is defined in linuxfs.h, the include file that we have mentioned here. Let's quickly see that file. So I'm just going to say gvim lib modules $uname -r, that's my running kernel, build /include /linux/fs.h. If you search for file underscore operations in this file, the fs.h file, so you see the structure here. Now we are basically interested in a few files. Who's the owner of the structure? What is the function for performing the read? What is the function for performing the write? What is the function for opening the device? What is the function for releasing or closing the device, right? So what I will do is, so I'm just going to close this one here. So we'll come back to our program here. So I'm just going to write a few functions for performing the file operations. So the owner field of the file operation structure gets initialized to this underscore module. The open function gets initialized to, let's call it as example 07 open. Then the read function gets initialized to example 07 read. Write gets initialized to example 07 write, and then the last release function gets initialized to example 07 close. Okay, so we have basically put 4 functions here: the open, read, write, close. Okay, now let's write the body of these functions. So what I will do is, so I'm going to open the lib/module slash dollar uname minus r slash build include linux fs.h. Okay. Is going to take the absolute path. So let's say split lib module slash the kernel folder slash build slash include linux fs.h. Now search for file operation structure on this. You found it here. So I'm going to copy the prototype of these functions, on what is the parameters and what is the return type of these functions. Okay, so I've copied them here. So now these are all function pointers that are registered. Now I'm going to give them the names that we have given. So open is going to be called as example07 open. Read is going to be called as example07 read. Write is going to be called as example07 write, and release is going to be called as example07 close. Okay. Now let's give the names for these parameters. So the first parameter is an inode. We'll call it as pinode. Second parameter is a file. We call it as pfile. Okay. And similarly here, so the first parameter is a pfile. Second parameter is the buffer. Third parameter is the length of the buffer. Last parameter is in offset. Similarly for the write, first is again a file pointer, then the buffer, then the size, and then finally the offset. And for close, it is basically the inode and the file. Okay. Now what we will do is we'll just put some prints inside these function to understand when they're getting called and when they're getting released. I mean, when actually the functions get called. Now open is a function which has to return a value, so we return 0 to indicate success. Read is a function, and we return 0 to indicate we don't have any data to return, so that is the file is empty. Write function, we simply say that we have written whatever is being requested by the user. See that this third parameter length indicates the number of bytes in this buffer that has to be written to the device, and we are saying that we have written everything. Though we are not actually doing it, we are just dropping the bytes and saying that we have written everything. And close, again we return 0 to indicate success. So that's it. So basically we have written 4 functions to perform the open, read, write, close functions. All of them are dummy functions. We have initialized the file operation structure with our own read, write, open, close functions. We have registered the character device driver here for a particular major number, and then when the module exits, we have unregistered the character device driver. Let's save this, and I'm going to open the make file. Before I do that, let's copy our file name. I open the make file, so go to the end of it and say obj-m := paste our file name and rename the .c with a .o. Let's build the module. Okay, so it says incompatible argument. Okay, so let's open the file gvm example 07 7.c. Register cadr, the last argument should be a pointer to the file operations. I'm just going to put an ampersand there, save it, compile it, and it's successfully compiled. So lsmod, let's see whether we have any of our drivers loaded. Nope. And so I'm going to say sudo insmod example07ko. It'll prompt you for password, give the password. Now when you do an lsmod, so we see that our driver is loaded. Now to confirm, we have actually got a driver for major number 240, and we get 240 because we have registered our we have used register cad with the first parameter as 240. So in order to confirm this, so what you can do is you can do cat of proc devices. So proc devices basically gives you all the drivers that are currently loaded in the system. So you see the character device drivers listed first, followed by the block device drivers. And so what it says is it has basically a two-column output, and the first column is the major number and the second column is the driver which is owning that particular major number. So if you see here, so we see 240 as a major number and simple character driver as the driver, which is nothing but what we have mentioned in these lines. So this indicates our driver is successfully loaded and it is linked to a major number 240. Okay. Now what we will do next is, so we have a /dev entry, and we are going to make a device entry here. So I do a sudo make node -m, which is basically for the permission, and I say everybody gets read-write access. I'm going to call this entry as /dev simple character device. It is a character device, major number of 240, minor number of 0. So if you do an ls -l of /dev simple character device, so this is exactly what you see here. So the C indicates a character device driver. Everybody gets read-write access. That is basically that 666 field here. And this is a 1 and created by root, belongs to root group. 240 is a major number, minor number is 0. It was created around this time, or rather last modified around this time. This is the name of the entry. Now what we will do is, I'm going to do a tail minus, or rather sudo tail -f of var log syslog. Okay. So we see our module init function that was invoked. Now I'll open another terminal. I will bring it down and slightly reduce the size of it. Okay. Now I want you to understand one thing. So when you do a cat on a particular file name, say for example cat test.c, so what you see here is the contents of the test.c file is displayed on the screen. So basically what cat as a program does is opens this file, reads the contents of the file, puts it on the screen, and then closes this file. So when I do cat of dev simple character device, so cat basically does not differentiate between a regular file and a device special file. So what it is going to attempt is it is going to open this particular device, that is /dev simple character device, read it, and then on completion of the read, close the device. So when I execute this command, so you see here inside the example07 open function, inside the example07 read function, and then example07 close function. On a similar lines, when you do an echo of say hello world and redirect this to a file, let's call it as hello.txt. Now what echo does is opens a file called hello.txt, writes hello world into this file, and then closes the file. So you can, when you do a cat of hello.txt, you see this contents being saved in the file. The contents that you passed before the greater than symbol here. So we're going to do the same thing here. So when I do an echo of testing and redirect this to /dev simple character device, so you see that the open function got called, the write function got called, and the close function got called. So this, in short, summarizes how a character device driver would work. So just to recap, so you have the module init function, which is called when the module gets loaded into the kernel space. So we have called the register cadr function, for a particular major number. We gave a name for the device, and then we have registered the set of functions, basically the open, read, write, close functions to be called when a device node corresponding to major number 240 is accessed, either for open, read, write, close, or like any operations like we saw with the cat and the echo programs. And when the module gets unloaded, that's basically they're removed from the kernel space. So we have done unregister of the character device driver, and we have said that we don't want to handle devices of major number 240 anymore. And we put a short dummy functions, so the open function, read function, write function, and close function, which basically indicate how indicates or demonstrates how the open, read, write, close gets called when we make an access to the /dev node. Okay. So I'm going to stop this video here, which basically gives you a quick understanding of how a character device driver is written, and then how you basically execute it by making an entry in the /dev file system. So just to show you the command again, so this is a command that we ran to create a node in the /dev file system. Like, so one sec. So basically ran the mknode command, and since we are making changes to the /dev file system, you need a sudo. So you said I want to make a special node, that's a mknode, with -m indicating the permission everybody gets. The name of the node, that's going to be /dev simple character device. Whether it's a character device or a block device, the C here indicates it's a character device. Major number of the device, minor number of the device. Okay. So I'll stop this video here, and hope you enjoyed watching it. So we'll again meet in the next video, or discuss some other topic in the next video. Thank you.